Alright, let's continue. Let me open the table of content first. We are still in chapter 17, still in homework simulation section here. Let me open that. Okay. Alright, this section, homework simulation, basically we are checking out the, the free space allocator simulation using this malloc.py script. We already take a look at this. We also already take a look at this, right? In the, in the first question, we use the best fit searching algorithm, and then on the second question here, we are using the worst fit searching algorithm to search the, the free space in the free list, right? Search the free list, and it looks like the worst fit can cause more fragmentation than the best fit, because the best fit might reuse the existing free chunk of space, but the worst fit will always use the largest chunk of memory, the largest free space, something like that. Okay, let me revisit that for a bit. Where is it? This one, worst fit, right? Find the largest chunk and return the request amount. So basically, we are splitting up the largest chunk, and that can and that can worsen the fragmentation, I guess, something like that. Most studies show that it performed badly, leading to excess fragmentation, right? We're still having high overhead. The high overhead in here means that we are still searching all the list, all element of the list. So let's say we have 6 chunk in the free list. We are keep searching every element in the list, every chunk in the list. So that can be, that can be heavy, I guess. So something like that. And then let's take a look at question 3 here. Alright. What is it called? Malloc.py, okay. Alright. What about using first fit? Okay. I think this is the default, right? Default value for this script. The default for sheet is 0 here, right? And then the default number of operation generated. The operation in here means the allocation and the free, something like that. The allocation of memory and free the memory. Okay, the default is 10, and then the header size default is also 0. Okay, so I don't think we need to provide this flag, and we can just provide this instead of base, which is the default. Where is it? This one. The default is base. We provide with force feed. Okay. VM free space. Okay, something like this. Let me check the info here. Yeah, we're gonna use this representation. Okay, heap is 100 from this one size, and then start address, this base address, and then header size is 0. Okay, alignment size also 0. Right, if it is -1, there's no alignment. If -1, if no alignment here. Right. Okay, policy first. Wait, release return order still address sort. Okay, and then this one is first. All right. Oh, wait a minute. Okay, 0, alright, 3 bytes. Okay. Okay, 2, maybe something like this. 0, alright. Okay. I kind of forgot what is first. Is it like, oh, the first block that is big enough? So instead of searching every element in the list until the last element of the list, we stop in the first block that is big enough. Alright. Okay, search one element, right? Because we only have one element here. And of course, this one is 97. Okay, something like this, right? Free. What is the representation here? Okay, size 2, right? Because we didn't coalescing the free space, we have fragmentation again. This one is 3 bytes. Okay, something like this. Okay, 97. Alright, PTR1. This one, unlock 5. Okay, header, 0 alignment. Oh wait, 5, right? 5 byte, and then return address. Again, from this free list we need to split this one, the 97 bytes of chunk, so maybe something like this until, okay, remember we start from this 3 4 5 6 7, right? So yeah, something like that. For header, alright, again, in case anyone still confused, I guess we start from this address 1003, 1004, 1005, 1006, and then 1005. So we have 5 bytes, right? Something like that. For alignment, right? And then free list size is 2, I guess, and then we search 2 element. This one is 1008, right? The next space after 1007 here, and then this one is, I guess, 92, something like this. Okay, and then we free again. Size is 3. This one is 5 bytes. Okay, something like this. And then yeah, we already done this, right? PTR2 now. PTR2 unlock, what is it called? Unlock 8. Okay, header 0 byte, 8 byte. Okay, and then alignment is 8 byte, the total with 0 alignment. Okay, and then the return address looks like we need to, what is it called, to split this again, the largest chunk of memory again. Okay, right. 1008 until 1015. 0 byte for header, 0 byte for alignment, and then free list. The size is 3, right? And then we search 3 element from the previous free list here, and then we split this. Okay, what is it called? Maybe 84, something like that. Okay, and then we free the ptr to here, right? Okay, size is 4 because again we already, what is it called, we already split this this large chunk. This one become 1016. Okay, and then allocate again for ptr3. Okay, ptr3 alloc egg 0 for header. Okay, 0 for alignment. Width is 8 byte again. Return address. I think we are gonna reuse this one, right? Again from the first feed here. First feed, the first block that is big enough. Okay, this is big enough, so we use that again. Alright, 0 for alignment, and then the release. Size is 3 and search 3 element. So instead searching the element in the list, we only search until we find the, what is it called, the memory chunk that is big enough. So we stop in this memory space. Search 3 element, and then let's copy this, something like this, and then free again. That is the same, right? Because we didn't split anything and just reuse this one, so there is no further fragmentation, something like that. And then ptr4 alloc 2. Okay, ptr4 alloc 2 byte. Okay, header 0 alignment, 2 bytes, and then return address. Okay, I think we need to split this one, right? Person, okay, and 1, 0 for header, 0 for alignment, and then release. Size, I think size 4, right? Because we split up this one, so the size is still the same, which means there is another fragmentation. Okay, yeah, we can only minimize fragmentation, I guess. And then search 1 element, because we immediately split this one other than searching other element too. Okay, something like that. that one. Okay. Alright, maybe something like this. And we have one byte here. And then we didn't free the PTR4 and just doing another allocation. Alright. Alloc 7 header alignment 7 byte return address. Okay. 7, huh? Looks like we need to split this one out. Okay, and then maybe something like this. 0 for header, 0 for alignment. Release size 4 because we didn't free anything previously. We didn't free the PTR4. Search the element. Okay, something like this. And 1 byte. Okay. At first this might look like similar to the base fit, but the search element is different. We stop after we find the, what is it called? The memory space that is big enough for the request size. Something like that. Okay. Let's try that out. The moment of truth. Okay. PTR0. Nothing interesting, I guess. Right. Still the same. It is still the same like previous allocation. Okay, previous, what is it called? Search policy of the free list. Okay, PTR1. Okay, search the element. Yeah. Search the element here and then splitting up this one, right? Here return this one. Okay, it's still the same as previous search policy. Nothing that much different, right? PTR2. Okay, I think PTR2 is also the same, right? Search the element here because there is no exact chunk of space or close enough other than this biggest one, so we need to split that up. Okay, it's also the same with the free PTR2 here, right? The interesting part starts at PTR3. Right. Okay, search 3 element, right? Return the same address or memory address here. Search 3 element and then have this one, the free list. Okay, are free to, what is it called? We are free to PTR3, alright. And then PTR4 here. Can we return 1000 as the address, the memory address, and only search one element instead of 4 elements, the previous free list, right? And then this is the reset free list. We are splitting up the first chunk of the free list here, but we only search one element. Okay, and then PTR5, we return this memory address, and then we search only 3 elements instead of 4 elements, and we are splitting up the third chunk in the free list, something like this. Okay, alright, this first fit. Okay, for the above question, how the list escape order can affect the time it takes to find a free location for some of the policies. Oh, use the different free list ordering. Okay. To see how the policies and the list ordering interact. I'm assuming the above question is this one, starting from the question 1 maybe, or maybe only question 3. I mean, the best and the worst doesn't really necessarily have an effect with the ordering, right? Because we are gonna search for every element in the list until the last element, so I don't think it has any effect how the ordering, how we order the free list for the best fit and worst fit. So maybe the above question here means the question 3 here, using the first fit or something like that. Okay, we already take a look at this address sort, and then we will take a look at this size sort plus and size sort negative. Okay, from this one, from the address sort, I mean, I guess it depends on the request size, right? If the request size is, what is it called, is small, maybe the sorting by the address is faster, something like that, kind of similar to the best fit, but what is it called, but we didn't search all the element, which means that we have a lot of fragmentation in the early chunk of memory, something like that. Okay, Well, let's try that out first, and then what is the ordering again? The flag to order. Oh, this one. L, list order. List order. Okay. Here to take a look at this one. Address sort. Sorting by the address ascending, right? And now size sort. Size sort plus first. Okay. Size maybe something like this. Alright. Should I just delete this? Maybe I should just delete that. Okay, still no header and alignment, right? Okay, I think this is the same. This is also the same. Wait, if that is the case, okay, PTR1 also I think the same, right? Nothing really different here. PTR2, yeah, okay, I split up this one, the largest chunk again, because there is no chunk with 8 bytes, right? Okay. Oh, wait a minute. No, it's not. It's not the same. Because size sort plus in here. I assume is ascending, right? So sorting by size but ascending from the, what is it called, the low or the small size until the biggest size. Maybe something like that. Okay, this is still the same. Alright. Okay, this is still the same too. Okay, this is still the same, I assume. Okay, we are just coincidentally having the same sort here. Okay, PTR4, right? Now I think this one is different. Something like this. Can sorting by size, right? We are sorting by this one. The size. From, what is it called? From smallest to the biggest in here. The size. Okay. Right. I think for this scenario, the only difference is this one, I guess. Well, let's find out. Okay, it's the same, right? PTR0, PTR1. Nothing that much different. ptr2 also the same. Okay, ptr2, ptr3, right? So 3 element, this one, right? Okay, alright, and then free ptr3, okay. Alright, still the same. We split this up. The first chunk in the free list. This one is different, I assume. Oh, wait a minute. Wait. It is not. Interesting. Wait. Let insert. Okay. Why is size sort still like this? I thought that the address 1015 will be on the second list. Is this correct? Right? I mean, if we are sorting by the size, this new address size. Oh, wait a minute. Are we not reordering the existing chunk? Is that it? We are only reordering the, what is it called? The new chunk after we free that. Let me try. How do I try this? Wait. Let me try using the alloc list. Instead of random list, use specific list. Okay, what is uppercase A? Okay. Plus 3 K plus wait a minute, plus 3 plus 5, right? This one plus 5 free that. If you are using negative prefix, we should use the index instead of the memory size, maybe something like that. Okay, and then egg byte. Alright, another egg byte. Okay, and then free that immediately. 2 and then 7 and then free the index 5. Free this one. Okay, let's see. Okay, this one, right? We didn't move this address. Okay, and then what happened after we freed that? Oh, okay. So is reordering happen when we free the previously allocated memory? Is that it? Interesting. So when we what is it called? When we take the allocation here, we didn't reorder the free list. I assume something like that, at least in this simulation. But after we what is it called? We free the allocated memory, we are doing some reordering. See, address 1002, address 1015. See, address 1015 on the second chunk here instead of the third chunk here. Again, this is the first chunk, this is the second chunk, and this is the third chunk. This is the first chunk, this is the second chunk, and so on. Okay, interesting. Let me add in the info here. Where is it? Looks like altering happens when freeing, I guess that's okay, the memory, not when allocating memory. Maybe something like that. Or let me put that in here. Oh no, let's just do it here. Do this, I guess. Okay. Interesting. So in this case, there is no difference between what is it called? Size sort plus with the address sort, I guess. That is something to keep in mind. Okay. Size sort negative. And then for size sort negative if here we are doing the reverse, right? Basically from the biggest to the smallest, something like that. Okay. This should be something like this, right? The biggest first, and then just one element isom, right? Okay, something like this. Yeah, I'm kind of curious what happened with the PTR3 when we have the same what is it called, the same memory allocation. Is it gonna be like the worst fit? I think it's gonna be like the force fit when we are using this size sort negative order of the free list, but let's see how it goes. I guess I might be wrong. Something like this, right? Okay, and then yeah, I don't think the address here will have any different. Search one element again, because because we are using this, the largest chunk. Okay, something like this maybe. No, this is the interesting part. What happened here? Are we gonna reuse this? I don't think so. So maybe something like this. That is the case. The return address in the PTR3 will be different. Okay, 16 until 23 maybe. Search one element, element, and this one 24. The size here is 74. Wait, no. Okay, 76. Right. Okay. I assume something like this, because again from the previous definition of first fit, right? Find the first block that is big enough. If we are ordering with the size sort negative, it is from the biggest size to the smallest size. We are gonna keep using the biggest size, like slicing this biggest size, I think, which can worse the fragmentation. Okay, right. Okay, kind of interesting. If we have the same byte of size, what is the ordering should be? Okay, for now I assume something like this. So like the second, what is it called? The second priority is the address space here. The memory address here. So the memory address that is bigger, I guess, is at the top, but the opposite can also be true, something like this. So yeah, I'm not sure yet. I mean, we will find out later on if this ordering is correct or not. Okay, and then PTR4. Alright, we are keep splitting this up. Yeah. Okay, maybe something. Wait a minute. Okay, maybe something like this. And yeah, the return address must also change. 24. Okay. 2. Okay, but that means 25 here. And then this one 26, I guess. Again, we also including this one 1024 and 1025, so 2 bytes, right? This one is 74. Okay. It is quite interesting. Right. Six, 7, huh? Okay, that means I think 32, maybe something like that. Okay, and then this one 33. Okay, 67 maybe, something like that. Okay, let's see if this is correct or not. PTR0. Okay, free this one. Right. Oh, sorry. The free PTR0 here. Okay. Allocation again. Right. We are keep. What is it called? We are keep splitting up the biggest memory, at least in this case. Free again. Okay. And then alloc again. Yeah, splitting this up, right? 1008. Okay. Free that. Alright. PTR3. Right, we split this up again. The biggest chunk here, rather than reusing the exact what is it called? The exact memory or chunk size. Okay. And yes, such one element, and then such one element again. At least the search is fast, but maybe in this case the trade-off is that we are having worse fragmentation, something like that. Okay, let's see how the ordering, if we have the same size of byte here. Okay, this is address 1024, right, with size 76, and then this one address, okay, so if the size is the same, we are doing something like this. We prioritize the smaller address first. Alright. Okay. Then this one, right? Nothing special there. Unlock again, allocation again. Chopping out the biggest chunk again. Okay. Yeah. Chopping up the biggest chunk again, right? So there is that. When we are using first fit, right? This first fit with the ordering the size sort negative here in terms of searching might be the fastest, but it also have the trade-off, like the, what is it called, like a lot of fragmentation here using size sort negative. As for this one, with the previous scenario using first fit, like this scenario, I don't really see any difference here. So yeah, maybe something like that. At least with the seed randomize 0, right? Again, from what I see, the sorting happen after we free the memory allocation, not when we do the allocation. So in this case here, I assume there is no difference. But if we free after the last allocation, we might have some different result. Okay. Coalescing of a free list can be quite important. Okay, I think let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.